So in section 8.2, we are discussing integration of trigonometric function. Well, a little bit more of advanced techniques, in which are really not that advanced. You know, it's only putting together the trigonometric identities that you learn in pre-calculus or trigonometry course, and put it together with some of the techniques that you already know from integration, such as the U-Substitution. Some integration by parts may come later, for sure, of course. So, well, we got a list of strategies here for the cases when we have cosine, odd powers of cosine, odd powers of sine. We already did one example of each. So let's have a look at another case. So last time we did a couple of exercises. We did an odd power of cosine, an odd power of sine. So today we have an even power of sine, and on top of that we have a what's it called, a definite integral. All right, well, so there's a couple of formulas that we're going to be using for even powers. Okay, let me scroll back again. So in this case, we're going to use the power reduction formula or half angle formulas, however you want to call them, that's fine. Well, so we have sine squared equals 1 minus cosine 2 theta over 2, and cosine squared equals 1 plus cosine 2 theta. Well, both formulas essentially look the same, except that the formula for sine squared has a negative, and the formula for cosine squared has a positive. All right? So that's how you might, in case you want to memorize these formulas and you want to use like a pattern recognition idea to memorize them well, you can distinguish them by their sign. So in this case, let's go to the exercise. Well, so we have the integral of sine squared, and well, unfortunately we cannot use a U-substitution here, because if we set u equals to sine, the derivative of sine is cosine. Well, but we don't have that power of cosine or factor of cosine multiplying with the dx, which stands the du part of the integral, so we can't do that. We have to use, in this case, trigonometric identities, and instead of writing it the quantity over 2, that's 1, I'm going to write it as 1/2 1 minus cosine 2x, and that's from 0 to pi. All right, so let's see. So, well, essentially here we're going to get two different terms. In the meantime, well, how about we take the 1/2 outside of the integral, and then from here, how about we write this in terms of two integral? That'll be a lot easier to see. So, well, that's a 1/2 the integral of the x from 0 to pi, and minus 1/2 the integral from 0 to pi of cosine to x with respect to x. Okay, well, the first integral, the integral of the x, well, that's just x, 1/2 x rather, don't forget about the factor outside, and well, minus 1/2 the integral of cosine, which is sine, 2x times another half. So the first half comes from the one that came from the identity, and the other half comes from integrating cosine of 2x. And then the whole thing from 0 to pi. So, well, let's reduce this product of halves. That's going to be 1/2 x minus 1/4 sine 2x. And well, the rest of the problem is fundamental theorem of calculus. Upper limit minus lower limit. So let's see what happens here. So that's for the upper limit, that's 1/2 pi minus 1/4 sine 2 times pi. Okay, and then minus, well, what's the lower limit? It's a 0. What would we get if we plug in the 0 here in the first term? 0. What about in the second term? Sine of 2 times 0 is sine of 0, which is also 0. So how about just big 0? That's fine. And well, in this case, what is sine of 2 pi? 0. All right, and our final answer here is pi over 2. Okay. Yes?
Why did you separate the 1/2 integral dx?
This 1/2
The dx?
over here. So to have two integrals instead of just one, because a very common mistake is to just focus on the cosine, you know, and then from there forget about this one, and then you would integrate only the 1 dx without the 1/2 in the front. So that's why I'd rather have this multiplying both factors and then, distributing that 1/2 and then integrate each term. All right? So let's see. All right, this one is going to take a really good minute to go. Well, so what do we have over here? Sine to the 4th power, cosine to the 2nd power. Well, number 1, do we have any odd powers? Of sine? No, we have even powers this time. However, be careful, because in this case we have sine to the 4th power and, well, the cosine to the 2nd power. It doesn't matter. Okay, let's go back and review these formulas. Okay, so we have power reduction formulas for sine squared and cosine squared. Actually, we're going to use both in this case. So, but before we can use both of these formulas right here, we need to rewrite the integral. Because in this case, well, sine to the 4th power doesn't really have an immediate identity. However, if we rewrite sine to the 4th power as sine squared, do we all agree with this? Power of another power, multiply the powers. Well, that's going to take us back to sine to the 4th power, and that times cosine squared x. Well, how are we going to do the substitutions here? Well, we have identities for sine squared. These will become 1 minus cosine 2x, all right, times 1/2. Well, you know what? Let me do this time over 2. I think it might be better. And this guy right here, cosine squared x, that's going to become 1 plus cosine 2x over 2. So we're going to use both identities here. Let's substitute. And, well, so a vast amount of the time for this exercise will be algebra. So, well, so let's just bear with that. So that's the integral of, number 1, sine squared, which is 1 minus cosine 2x over 2, times cosine squared, which is, oh, that's squared. Don't forget the square, because we broke up the power of sine to the 4th. And then that's 1 plus cosine 2x over 2 with respect to x. All right. So in this case, well, let's do some algebra. Well, so number 1, you might want to square numerator and denominator using laws of exponents and rewrite the integral as the integral of 1 minus cosine 2x quantity squared over 2 squared, which is 4, times 1 plus cosine 2x over 2. All right. And, well, how about we take care of the numbers in the denominator? This way we don't have to end up with fractions, and we don't have to combine numbers in terms of fractions when we simplify this integral. So 4 times 2 in the denominator, that means a 1/8, but that 1/8, I'm going to write it outside of the integral. And at the same time, well, I'm going to do some algebra over here. And again, there's a couple of ways to simplify this 1 minus cosine 2x quantity squared. Number 1, you might want to write it and multiply it with itself, then FOIL, which is fine. It's a little time consuming. Or you can use simply the the square binomial formula, which we already discussed a couple of times. So that's a squared plus or minus, depending on the case, 2ab plus b squared. I think it's shorter to do this, so I'm going to do that operation on this factor in the numerator. And then whatever we get from there, we will, yes, for this, we will have to FOIL with the next factor. So we're going to get for this, number 1. 1 squared, which is 1, minus 2 times the product of the two terms, that is 2 cosine 2x, and plus cosine squared x. And then the remaining 1 plus cosine 2x will just remain there. All right. Oh, this is supposed to be 2x. Okay. With respect to x. All right. So yes, this is going to be a lot of distributive property. Okay, let me show you how are we going to do this. So one at a time. 1 times 1, 1 times cosine 2x. All right. So that's the next term. Don't forget about this 1/8 in the front. So 1 times 1, which is 1. 1 times cosine 2x, that's cosine 2x. And then let me do the second distribution. That's negative 2 cosine 2x times 1, and negative 2 cosine 2x times cosine 2x. So that's negative 2 cosine 2x minus 2 cosine squared 2x. All right. And the last of the distributions would be with the cosine squared times 1, cosine squared 2x times cosine 2x. All right, let's go ahead and do those. So that's going to be plus cosine squared 2x and plus cosine cubed 2x. Alright, before attempting to do any integration, how about combined like terms, if any? Alright, and I think there's a number of like terms. For example, cosine 2x with cosine 2x, to the first power, they're like terms. We'll combine them together. And also cosine squared to x, cosine squared to x. In this case, to the power 2, they're also like terms. So let's combine them together. Well, in this case, this is the only constant that we have, and this is the only cubed power that we have. So we'll leave them alone. So let's just combine the other two terms. So let's see. That's 1/8. The integral of 1, so cosine 2x minus cosine 2x, that's going to give us negative cosine 2x, and negative 2 cosine squared dx, cosine squared 2x plus, so that's a negative 2 plus 1, that's a negative 2 cosine squared 2x. And well, this cube, just write it down. Okay. So what do we have so far? Question? The cosine squared 2x. Oh yeah, should be negative only, right? Yeah, just negative. Okay, thank you. Okay, so what do we have for now? We have, if we distribute this integral into 4, which is the next step, we would be able to integrate 1 dx, which will be x, and we will be able to integrate cosine to x. Well, that's easy to, those two are easy to integrate. However, over here, the last two terms will require to use the strategies that we have been discussing since the beginning of this section. Well, we're going to use, again, the power reduction formula, and we're going to use the odd power strategy here, in which we will have to same one of the powers of cosine, and write the remaining factors in terms of sines, because that power of cosine that we will be saving will stand the du part of the function that we will be rewriting. So let's do one thing at a time. So what I'm going to do, I'm going to write for integrals. That's 1/8 integral of dx minus 1/8 integral of cosine 2x minus 1/8, don't forget the 1/8 in the front, cosine squared 2x plus 1/8 integral cosine cubed 2x. Well, actually, you know what? In this same step, I'm going to write this cosine squared 2x times cosine 2x dx. Okay, let me write down what are we going to use in this case. So here we're going to use the Pythagorean identity. We are going to replace cosine squared to x equals 1 minus sine squared to x. And that comes from the identity sine squared plus cosine squared. This is 2x actually. Recall that these identities, sine squared theta plus cosine squared theta equals 1. This identity is valid for any real valued angle, like for example 2x. It's valid for sine squared x, cosine squared x, 7x, 5x, and why not 2x? So of course it's valid for also for 2x. And what are we going to do here? Well, so for the previous integral, for the third integral, we're going to use a power reduction formula because we have an even power of cosine, not an odd power. So in this case, be careful about what's going to happen here, because this cosine squared 2x, yes, we're going to use this power reduction formula, 1 plus, but what happens to the angle every time that we use this power reduction formula? Let me go back to the formula part. Okay, observe what happens with theta. What happened from here to here? Loud, please. It doubled, right? It doubled. Well, so in this case, same thing. It's going to double, and we're going to have cosine of 4x in this case over 2. All right. Well, yes, we will be writing a good number of integrals, but don't worry, we're almost there. We're almost there with this one. So that's 1/8 integral dx minus 1/8 integral of cosine to x dx minus 1/8 integral of 1/2 times 1 plus cosine 4x dx, and this integral will become 1/8 integral of 1 minus sine squared to x, and adjust that, cosine to x dx. Okay, so let's simplify this. Number one, I'm going to write this into two integrals, but at the same time I'm going to multiply the 1/8 with the 1/2, and that will become, well, you'll see, that's going to become 1/16, the integral of dx when splitting with the first term, and then when distributing with the second term, this will become 1/16 integral of cosine 4x dx. And in this case, well, I'm going to leave this integral the way it is like this, because in this case we're going to use a U-substitution, and this is going to work really nicely when we do that. All right, so let me just leave it as yes, that's 1/8 the integral of 1 minus sine square root 2x cosine 2x dx. Okay, so before attempting any integration, we're gonna have another set of like terms. So we're going to combine these two integrals, this one with that one. So 1/8 minus 1/16, that's going to give us a 1/16 minus 1/8 integral of cosine 2x dx, and well, we already combined these two, minus 1/16 cosine of 4x plus 1/8 integral of 1 minus sine square root 2x cosine 2x dx. Well, the first three integrals we can evaluate them in an immediate form. However, we need to set up a U-substitution for the very last integral, which I'm going to show right below. So in this case, u equals sine 2x du 2 cosine 2x dx. That means cosine 2x dx equals to 1/2 du. Alright, we're going to do the u substitution for this last integral. Well, so in this step I'm going to integrate these the first three integrals. So that's a 1/16 x minus 1/8 times 1/2 sine 2x. That's the integral of cosine 2x. The integral of cosine 2x is sine times that factor. That's a 1/2 rather, and minus 1/16 the integral of cosine, which is also sine, but that times a fourth. And in this case, we're going to have the following integral still, but in terms of u. That's the integral of 1 minus u squared, and this will be 1/2 du. But this 1/2 du will go outside and multiply with the 1/8 to become 1/16, 1 minus u squared. And let me just write this again. And simplify the coefficients also. 16 times 4 is that a 1/64. And well, so let's just integrate 1, which is going to be u. 1/16 u minus 1/16 u cubed over 3 plus c. Everything else remains the same. And all we have to do here is back substitute for the quantity u. And we said that u equals to sine 2x. So that's a 1/16 x minus 1/16 sine 2x minus 1/64 sine of 4x plus 1/16 u, which is sine 2x, and 16 times 3 is that 48, I think, 1/48, and sine cubed of 2x plus c. Alright, but check this out. This is going to get a lot simpler because these two terms are like terms. And our final answer will be, do I have enough space? Okay, let me make some space. This will be 1/16 x minus 1/64 sine 4x minus 1/48 sine squared 2x plus c. Final answer. So yes, as you can tell, these kind of exercises may become long due to the number of times we have to use identities, and well, how this, give rise to many terms and the like question.
What if the sine cubed 2x changed to sine squared 2x?
This one right here?
Yeah.
Well, oh, yeah, this is supposed to be a cube. Thank you. Yes. All right. Let's see what's next. Well, so the next is the strategies to evaluate integrals involving powers of tangent and powers of secant. Well, so in this case, the strategies for this kind of integrals are really not like all set like we had those for sines and cosine. For sines and cosine, you can't go wrong with those. I mean, even powers, power reduction formula, odd powers, well, save one power of the given trigonometric function to make the stand for the du part of the integral. Those are, I think, easy, so to speak. I mean, unless you get something long like the previous example that we just covered. However, these kind of integrals are not like the most, like, like the guidelines are not like already down. So we're going to use some of the strategies. Well, so whenever we have an even power of secant, what we do is save one power of secant squared, and the reason for that is because secant squared is the derivative of what function? Anyone? Secant squared? Tangent, right? So in this case, what we're gonna do is write the remaining powers of secant in terms of tangent, and then let u to be the tangent function. When we do the du part, that's going to be the secant squared x, which is the power of secant squared x that we saved to do the U-substitution. In a similar way, whenever we have odd powers of tangent, we saved a factor of secant tangent, and in this case we use that identity the other way around. Tangent squared equals secant squared minus 1. And that's because in this case we will write everything in terms of secant, and the derivative of secant is secant squared, and that factor that multiplies the dx will set the du part of the problem. Alright, so let's have a look at one example so we can see these powers in action. Well, notice in this case we don't have two cases for it. We don't have odd powers of secant. Well, we will later, but those are going to be different, you'll see. And we also we don't have an even power of cosine case, of tangent, like we had both parity of powers for sines and cosines. So that's why I'm mentioning the strategies for powers of tangents and secants are not very well established in the same way the ones for sine and cosine are. So let's have a look at one example. What do we have? Tangent to the 6th power, secant to the 4th power. Well, number one, do we have an even power of secant? That's the question. Yes or no? Yes. Well, so the rest doesn't matter. So, and lucky for us, we have an even. Well, yes, we have an even power. We will break this up into the integral of 0 to pi over 4. It's going to be a definite integral as well. So that's tangent to the 6th power. Secant. I'm going to write this secant to the 4th power of x as secant squared times. I'm going to use a different color, so you can see the power of secant squared x that I'm saving for later, so we can use it to set the du part of the problem. Alright, that means that we can use the secant squared formula, or rather secant squared, to write this secant squared in terms of tangents. Alright. that's the integral from 0 to pi over 4, and that's a tangent to the 6th, and that's 1 plus tangent squared. Space. Secant squared x dx. Well, so how about we distribute this tangent to the 6th right here, so we can have individual powers of tangent. That's going to give us the integral from 0 to pi over 4. That's a tangent to the 6th plus tangent to the 8th times secant squared x dx. And at this point, we may go ahead and go through the U-Substitution. U equals tangent, and the derivative of tangent, which in this case is secant squared. And that's the reason why we saved 1 power of sec, or rather 2 powers of secant, because secant squared, it's actually the derivative of tangent in a similar way that we did in the previous set of strategies for sines and cosine. We saved 1 power of sine or 1 power of cosine, so we can integrate sine and cosine by, setting this u to u part. That means we can integrate this like so. Let me just write the integral without the limits, and that's u to the 6th plus u to the 8th du. That's u to the 7 over 7 plus u to the 9th over 9. Evaluate all. Let me go back, substitute first. That's a tangent x over 7, quantity to the 7, and tangent x to the 9 over 9. And now let's put the limits of integration, 0 to pi over 4. Well, so number 1, tangent pi over 4, quantity to the 7th power over 7 plus tangent pi over 4 to the 9 over 9 minus, well, what would happen if we plug in the lower limit of 0 to the tangent function? What's tangent of 0? 0, so just big 0. That's fine. And well, on the other hand, what's tangent of pi over 4? Is that a 1? Yep. So that's 1 to the 7 over 7 plus 1 to the 9 over 9. That's 1/7 plus 1/9. Then I left a space here to find common factors so we can combine the fractions together. That means 9 times 7, is that a 63? And in the numerator, 9 plus 7, is that a 16? And its final answer for this integral. All right. It's still a long way before we finish this section. I thought we were almost done. Anyway, let's look at one more example. So I'm trying to cover like pretty much at least one example of every single case, so you can have an idea of how to tackle the problems on your homework, on your quiz, on the exam once you get all this down. So let's see. We have tangent to the 5th, secant to the 7th. Well, this time we have odd powers. Well, for both, let's go back to the strategy guide right here for odd powers. Well, the only one that has an odd, that calls for odd powers, rather not odd functions, odd powers is whenever we have a tangent. And what do? Get a factor of secant squared, so we can write everything in terms of secant. And when we set u equals to secant, the du will be secant tangent, because the derivative of secant is secant tangent. In a similar way, we will number 1. So that's going to be equal to the integral tangent to the 4th, secant to the 6th, and notice how I am saving 1 power of each. Secant tangent d theta. And then from here we're going to use an identity. Which identity we're going to use? Well, let's go back to the previous page. We're going to use this identity here. We will replace tangent squared with secant squared minus 1. Alright? Well, actually before moving on through this example, well, of course, the identity that you know the most is the sine squared plus cosine squared equals to 1. That's the basic Pythagorean identity. And well, of course, it's all its implications. But sometimes we will be in the need of using the other Pythagorean identities that involve secant and tangent, or cosecant and cotangent. And unfortunately, those we don't memorize very well, as or we don't use them as often as we use the sine squared plus cosine squared. So let me give you a trick to memorize or to actually obtain those identities. For example, we can start. Let me write it twice. And I'm going to write S for sine and C for cosine to keep it short. S squared plus C squared, that's sine squared plus cosine squared, that equals to 1. That's the identity that we know the most. And I'm going to write it twice because we're going to obtain 2 new identities. Well, the trick here is, in the first case, to divide all terms by sine squared and divide both sides by cosine squared on the second case. Well, what's sine squared over sine squared? 1. What's cosine over sine? Cotangent. And 1 over sine? Cosecant squared. And that's how we get that identity. The other identity that involves tangent and secant, well, what is sine over cosine? Tangent. And cosine over cosine, well, that's 1, and 1 over cosine, secant squared. So just in case you are on an exam and you are in the need of using those 2 identities and you are not provided with those formulas, well, a good way around, start with the sine squared plus cosine squared equals 1 and derive them by dividing by sine squared on one case and derive by cosine squared on the other case. So, or I mean, if you have them memorized, well, that's fine, but it's always good to go back and check this out. All right, so let's go back to the integral, and well, so we will replace we will replace everything in terms of secants, and that's because we have a secant tangent factor to use it later as the du part of the problem. So over here, then we're going to use not yet, because we have that tangent to the 4th power. So this will be the integral of tangent squared theta quantity squared, in a similar way that we did with the other problem, the problem we begin with today. So sine, not sine, actually secant, right? To the 6th and secant tangent. All right. And well, that tangent squared will become, in terms of secant, will become secant squared minus 1 by one of the identities. It's listed in the strategy guide in the previous page, but again, if you want to derive, well, I already gave you the trick to derive them. Okay, so let's write this down as, let's replace, that's the integral of secant squared theta minus 1 squared secant to the 6th power. times secant tangent d theta. So let's see. Well, at this point, there's a couple of ways to keep moving on. Number one, squaring the binomial and then having individual integrals. Or we can actually do the U-substitution at this point because we already have everything in terms of secant. So, and that's what I'm going to do instead. So u equals to secant theta du will be secant tangent d theta. And while rewriting the integral, it's going to give us the following. That's the integral of u squared minus 1 squared u to the 6 du. And I think it's easier and shorter to manage this binomial square rather than having all in terms of trigonometric functions. Either way should be fine. However you feel more comfortable with, as long as you get the same result, there is nothing wrong with doing it one way or the other. So that's the integral. Okay, quantity. Let me recall the formula for the binomial square. That's a plus or minus b squared. That's a squared plus or minus 2ab plus b squared. And that's u to the 4th minus, in this case, 2u squared plus 1. And that times u to the 6th du. Recall this du became secant theta tangent theta by our U-substitution. And in this case, well, let's distribute the u to the 6th to get u to the 10th minus 2u to the 8th plus u to the 6th du. And at this point, we can integrate every single term. That's going to give us u to the 11, 1 over 11 u to the 11 minus 2 u to the 8 over, u to the 9 over 9, and plus u to the 7 over 7 plus c. And all we do from here is do the back substitution for u, which we did. That was a secant. So that's going to be 1 over 11 secant to the 11th minus 2 over 9 secant to the 9 plus theta plus 1 over 7 secant to the 7th theta plus c. Right? And that's another example on how we use integration of trigonometric function, but this time one case in which the power of tangent was an odd one. And in this case we had to break it up into, or rather save a factor of secant times tangent, so we can use that as the du part of, in this case, secant. And we do that by later writing the remaining factors of the integrand in terms of secants. Alright? So let's see, let me check what's next.